All right, we are now on the second video for chapter 15. Again, we're looking at acids and bases. We looked at electrolytes in the first video, and now we're going to move on to some definitions. All right, so first definition, let's look at acids. You probably recognize acids a little bit by their sour taste. You can think of orange juice or any other citrus fruit that has citric acid in it. All right, we also can look at how an acid is a solution that will indicate, okay, if it's an acid or a base on litmus paper, and for acids, they turn litmus paper red. There's also reactions that acids tend to make with metals, especially the active metals, if you remember from our activity series. They'll react with active metals by producing hydrogen gas. Okay, so there's a couple little things about the acids in general, and we've looked at their definition in previous lectures as already when we looked at acid-base reactions. The Arrhenius definition of an acid says any electrolyte, okay, we just hit that definition the other day, is one that contains one or more hydrogen atoms, okay, so it has to have a hydrogen, and when it's put into solution, okay, added to water, it will produce H+ ions. We already talked about how H+ ions will then join with the water and form the H3O+. What is H3O+ again? Hydronium ion. Oh, and you can see that right here. So here's the hydronium ion. What happens to the H+ in water? All right, so we can then look at this definition and say, okay, here is some HCl, so hydrochloric acid. If we add 1 mole of it into solution, okay, on the product side, we now have formed H3O+ and Cl-. 1 mole of the acid breaks apart into 1 mole of the H+ and 1 mole of the Cl. That indicates to us that this is a very strong acidic solution, so it's a strong acid and it completely dissociates. This reaction goes completely to the right and it has a very high equilibrium constant. All right, example of another acid that is a weak acid. We've looked at HF already. You take 1 mole of hydrofluoric acid, you put it into solution, and it does dissociate into ions. However, if you look at equilibrium, the concentrations of the reactants versus the products, you can see this is very reactant favored. You mostly have HF left, okay, in solution, the molecular compound that didn't dissociate, and only a small amount of it did dissociate. So reaction lies to the left, a weak acid based on that, but you still make some hydronium and some F-. So since it does make a H+ or hydronium ions in solution, it's still considered an acid, but it's a weak acid. Here we go. Let's just look at what happens here. This is the picture here. Here's the H+, here's the OH-, showing you our hydronium. So when you see or hear me say proton, a hydrogen proton, or if I say H+, or if I say H3O+ or hydronium ion, you're kind of thinking the same thing. So a hydrogen proton would be a hydrogen atom that's lost its electron, so it just has its proton left. And then H+, same thing there, and H3O+ is just what happens to it when it's in water. One other quick thing just to recognize that acids have to have 1 or more hydrogen atoms. If it just has 1, in both of these cases that we just looked at, HCl and HF, there's only 1 hydrogen in the formula. All right, so those we consider to be monoprotic. So for example, HCl has 1 hydrogen. It is monoprotic. You can also have them being diprotic. What's the name of H2SO4 aqueous? Okay, a little definition or recall there on your naming of acids. When you have a polyatomic ion that ends in ate, such as sulfate, when you make it into an acid, you change the ate ending to ic, so this is sulfuric acid. Remember, you add the hydro only if there's no oxygen in the formula for the acid. All right, so sulfuric acid has 2 protons that could be lost. So this would be diprotic. Okay, that protic there stands for protons. Okay, how many protons it can lose. And can you think of a triprotic acid? Which one would be triprotic? If you're thinking back about your polyatomic ions, can you think of one that has a -3 charge? So it would need 3 protons in order to get the formula correct. hopefully you thought of phosphate, which is PO4 negative 3. So it would need H3PO4. Now, two little things here. First off, okay, usually the first proton is easy to lose. Okay, so high equilibrium expression for that. So that one's always easier. The more protons you have, it tends to be a little bit harder. So like for sulfuric acid, that first proton to come off, okay, would be considered a strong acid. And then the second one, when you have HSO4 minus, it gets a little bit harder to pull off that second one. So that's one thing. Another thing is, to be monodiprotic or triprotic, you have to have a proton that will be lost, okay? There are things that have protons, CH4, that has a proton. However, those protons will not be lost in solution, okay? It's not considered an acid, partly because that bond between the carbon and the hydrogen is more equally shared. So you need to have a partial positive on the proton in order for it to be able to get lost, come off and form H plus ions in solution. Acetic acid. All right, this is called acetic acid. Just a quick little thing, side note here. How many protons do you see total, or how many hydrogens do you see total in acetic acid? You can say, well, there's CH3, and then at the end there's another H, so there's a total of 4 hydrogen atoms here. However, in order to be an electrolyte, okay, you have to have that hydrogen has to be able to be pulled off when put into water. Again, here, this one, you have the hydrogens on this carbon. Those are not going to get pulled off, right? Okay, there's not a difference in electronegativity there. We have a C, double bond O, and an OH. Here, you can see there's going to be a difference in electronegativity. The oxygen's going to be partial negative, the hydrogen's going to be partial positive, allowing this bond to be broken, and you can then pull off this proton. So even though CH3COOH has 4 protons, this would still only be considered a monoprotic acid, since only 1 proton would be pulled off in solution. All right, that was a lot of information about that. Let's look now at the bases as well. All right, so characteristics of a base: they will taste more bitter. They react with litmus paper as well. They turn it blue. And when you are dealing with bases, they often feel slippery to the touch, and sometimes you don't even know you have them on you until you wash your hands. You're like, oh, it's very slippery. But they are corrosive, so you want to be very careful. A lot of cleaners have basic properties. Definition. We have looked previously at the Arrhenius definition of a base, and that says it's an electrolyte. It means it dissociates into ions, and it usually contains a metal ion and a hydroxide group. And so when you put it into solution and it breaks apart, it will produce hydroxide ions in solution. If you look at this common metal bases here, you can see you have group 1A and group 2A metals, all with a hydroxide. So the 1A, okay, those would be, all have 1 OH with them. And the 2A, so magnesium, calcium, barium, for every 1 magnesium, there's now 2 hydroxides just to balance out the charge. So those are all the 2A metals. Common ones that you should be familiar with. They can be strong or weak. Okay, these ones are usually, they're strong bases. And we'll talk about a couple weak bases, and there's one that you'll have to be able to recognize. That will be on the next slide, I believe. We'll get into that in a second, but just so you can verify, take some base, sodium hydroxide, add into water. By definition of the Arrhenius definition, this should produce hydroxide ions in solution, which we see here. All right, then, I think before we talk about the other one, we're going to quick talk about neutralization reactions. Another definition: acid and a base will come together, and they will make salt and water. This we talked about in chapter 9 when we looked at different reactions, and you probably have done this already. So we can see HCl and NaOH. You identify the H here with an anion, so you should identify this as your acid. And then you can see that this is has an OH, okay, a metal with an OH, so you should identify that as your base. And then we're going to make water and a salt. Now, what type of reaction is this? You have a cation, anion, plus another reactant that has a cation and an anion. You should think, oh, hey, we're going to be switching some partners here. Cation from one is going to join up with the anion from the other. So if we take the cation from HCl and the anion from the NaOH, we're going to put an H and an OH together, which forms water. And then what's left over? We have the anion from the acid, the Cl, and the cation from the base. All right, so our exchange reaction, or our double displacement reaction, we produce NaCl, and this is going to be soluble. So aqueous right there. So when you add sodium hydroxide and hydrochloric acid together, your solution should be neutral. We neutralized, we had equal amounts here of acid and base added. So all of the H3O pluses over here and all of the OHs over here join to make water. Let's see, if we want to write net ionic equation out, that's probably a good thing to do still too. Take the HCl, we're going to have H plus Cl minus plus Na plus OH minus reacts to give us H2O. It is a liquid, so in the net ionic or in the ionic equation you cannot dissociate that. You have to keep that together. And our ionic compound is soluble, so it's Na plus Cl minus. Anything that is on both sides we would cancel out and not include that in the net ionic. So we have H plus, which we know joins with water to form the H3O plus. So that's that right here. And then we have OH minus. And then in the end, we're going to be making water. We already added an extra water here, so that's why you can see two waters. All right, so that should be good for showing neutralization reactions. And that's a pretty good start for our definition of acids and bases using Arrhenius. However, we're going to get to the next one. I keep jumping ahead on us. We're going to quick talk about neutralization reactions one more time and actually do a problem with it. All right, here you go. This is what we're going to do. Barium hydroxide. If you have a reaction and you're neutralizing barium hydroxide with hydrochloric acid, can you figure out how many moles of the barium hydroxide is necessary, and can you name the salt? All right, let's see. We have barium hydroxide. Just by looking at the formula, you can label that as an acid or a base. You would say, oh, I see OHs there. I'm going to call this the base. And then HCl by its name, or by looking at the formula, you can say this is our acid. This is going to react. We're going to produce barium chloride. Now you don't want to try to balance it by writing the formula. You write the correct formulas, then you go back and balance. Since barium's a +2 and Cl is a -1, it's going to be BaCl2. And then what else is left over? The OH and the H+ have come together and formed water. Put a couple little coefficients in there to balance. Put our states there, and we should be ready to answer this question. All right, we are asked for moles of the barium hydroxide, and we're also asked for the name of the salt. Let's give the name of the salt really quick. This would be barium chloride. And then let's do the other answer. We are starting with 0.5 moles of the HCl. And how do you go from moles of one reactant to moles of the other reactant? You need to know the balance equation and the mole-to-mole ratio. There will need to be 2 moles of HCl for every 1 mole of barium hydroxide. You probably could do this in your head, but just to set it up to show with units canceling, if you start with 0.5 moles of HCl for every 1 mole of barium hydroxide, you needed 2 moles of HCl to react. And you can see that from the formula. There's 2 OHs for every 1 barium hydroxide, and there's 1 H+ for every 1 HCl. All right, so moles of HCl cancel when you divide by 2, and you get 0.25 moles of barium hydroxide. There we go. That was fairly simple. You might be given not just moles of HCl, you might be given a volume and a concentration, and you'd have to get to moles first. So lots of ways to ask us. All right, the next slide, I promise, we're going to get to this other definition of acids and bases, so hang with me there. That's it for this one.